This is for those who believe in the potential of science, making brave choices, choosing to push the boundaries. This is why we believe in what science can do.
Hello, good afternoon everyone. It's a great pleasure to be with you here in DC. I'm still on Scotland time, so forgive me if I get a little bit jet lagged during my talk, but hopefully you'll be able to cope with my Scottish accent, not too badly. So what I'm going to do in this session is to, as we heard from Bob, share with you some of the excitement that we've been generating and experiencing in these last few months as we've announced to the world the discovery of gravitational waves. And I guess it's quite appropriate that I should be here at the Science and Engineering Festival, which is all about sharing the excitement of scientific discovery with everyone. And of course, scientists get excited by all of this too. I'm the head of the School of Physics and Astronomy at the University of Glasgow, and a long time ago, one of my predecessors was known as Lord Kelvin, William Thomson, one of the most famous physicists there's ever been. And he used to get really passionate and excited about science as well. And he said that you could experience the beauty and the excitement and the amazing power of the universe just in our everyday lives, just in things that we look at around about us. Now, if you've not heard of Lord Kelvin before, you maybe know the name if you're a fan, like me, of Star Trek. Because in J.J. Abrams' movie in 2009, at the start of the movie, the spacecraft that's destroyed by those Romulans was known as the USS Kelvin, which suggests that Lord Kelvin will be just as famous and just as important a scientist in the 23rd century as he was in the 20th century. Now, he's still pretty famous and important in the 21st century, but the discovery that we made is one which I think Lord Kelvin would have been really amazed by, because it represents some measurements and some areas of physics that really we just didn't know anything much about when Lord Kelvin was around in the later years of the 1800s. In fact, you might say it sounds more like science fiction than science. But if there's anything I've learned as an astrophysicist in the last 25 years, is that the real universe is, if anything, even more amazing than what science fiction has dreamed up. And that's a Star Trek and a Star Wars fan saying that. So, it takes a lot to admit that the real universe can be even more exciting than Star Wars. So that's what I want to share with you today. What I want to do is to tell you about this discovery of gravitational waves that we announced in February here in DC with a simultaneous press conference in Italy and many other press events around the world, including one in Glasgow where I'm based. And I'm part of this collaboration, the LIGO scientific collaboration, which was at the forefront of this search for 100 years for gravitational waves. Well, LIGO's only been around for the final few decades of that, but Einstein's prediction that gravitational waves exist goes all the way back to 1916, which was 1 year after he developed a theory of gravity called general relativity. So it's quite appropriate that we should make this discovery in the centenary of general relativity. So what I'm going to do is tell you something about what gravitational waves are, how we can measure them, how we can detect them, and what they hopefully are going to tell us about the universe. And in fact, they've already begun to tell us some pretty amazing things through the collision of two massive black holes that we heard about in the introduction. And I'll tell you much more about that in a few minutes. So let's begin with the story of gravity, not in the time of Albert Einstein, but a few hundred years ago with Isaac Newton, another very famous physicist. And there's a story about Newton where he was sitting under a tree and an apple is supposed to have fallen on his head, and that inspired him to come up with a theory of the force of gravity. Now, we don't know if there was really any falling fruit involved, but the force of gravity that we get from Newton is packaged in a form of mathematics which is very powerful. We can use that idea of a gravitational force and the equations that describe it to do all sorts of things, to fly from Scotland to DC on an aircraft, to send a spacecraft all the way to the moon and back. But when you really think about what gravity is, that's where Newton's picture starts to be a little bit problematic. And it's because, according to Newton, there's this gravitational force which causes apples to fall from trees and causes the moon to orbit the Earth. And that works just fine as a mathematical description of how things move and how things fall. But if you want to really, truly understand what gravity is, then you have to kind of face up to a philosophical question, which is, how does the moon know it's supposed to orbit the Earth? How does the gravitational force actually reach out from the Earth to the moon, making it orbit around us? So, the person who tried to tackle that question and came up with a very different way of thinking about gravity was Albert Einstein. So he was a hugely important figure in science, and in fact, in 1999, Time magazine voted him to be the person of the 20th century. I should add that that was the editorial board's decision, and there was also a public vote, and the public voted for Elvis Presley. So you can decide who got that one right. Now, I'm a big fan of Elvis as well, but I think I would still have voted for Albert Einstein because of the important science that he helped to develop in the early 20th century, his theory of gravity, his theory of relativity. In fact, I'm such a big fan of Einstein that I have an action figure of Einstein on my desk in Glasgow. And last time I was in DC, I got a photograph of myself sitting on Einstein's knee. So he's been a very important figure in my own scientific career because I've worked on theories to do with Einstein's understanding of gravity and cosmology and the whole universe throughout my career. So what did Einstein have to say about gravity? Well, what he said was that we should think of gravity as a bending or curving of space. So instead of thinking of a force reaching out across the universe from the Earth to the moon or from Isaac Newton to that apple, instead we think of the presence of massive bodies in the universe curving the very fabric of space and time themselves. And there's a neat way to think of this. It's a kind of a metaphor. It's not perfect, but it's quite useful, I think, is to think of what would happen if you take a heavy object and place it on a stretched sheet of rubber, like a trampoline. It's going to cause the heavy sheet to deform and bend. And that means when another object comes along nearby, it's not going to follow a straight line. It's going to follow a curved path because it feels the curving of space and time around that massive body. Now, there's another physicist who captured this idea quite neatly. His name was John Wheeler, and his phrase is shown there on the slide. He said that space tells matter how to move, and matter tells space-time how to curve. So the presence of matter in the universe produces that curvature, and then other bits of matter are affected by that curvature. Now, you might think, what's the big deal? I don't notice that space-time is curved. But actually, it does have an effect, even on our everyday lives. Maybe some of you have seen that movie with Tom Cruise, Mission Impossible Ghost Protocol, where he's climbing the world's tallest building, the Burj Khalifa in Dubai. Now, I'm sure Tom was much too busy to notice, but when he was 800 meters up at the top of that building, his watch would run a few billionths of a second faster than the same watch down in the ground, because time runs faster in a weaker gravitational field. Again, a few billionths of a second per day is no big deal. I'm sure Tom wouldn't have noticed anyhow. But many of you, I'm sure, will have a smartphone with GPS capability. In fact, I used that to help me find the convention center when I arrived last night. And that smartphone uses microwave signals which come from the GPS satellites, the Global Positioning System satellites. And those are so high above the Earth that time runs faster for those satellites. It runs faster at the rate of about 40 microseconds per day. That's 40 millionths of a second. And microwaves can travel a few miles in that time, about 10 miles or so. So if we didn't take account of the fact that time runs faster high above the Earth compared with the surface of the Earth, your smartphone GPS wouldn't work. And I would have got lost coming here. So thanks to Einstein and general relativity, I got here, and I'm able to tell you about gravitational waves. Now, what exactly are gravitational waves? Well, let's think not of Tom Cruise and the Burj Khalifa, but of taking gravity to the max to an object where the curving of space and time is so strong that even light can't escape. And that's you got yourself a black hole. So the curving idea, the stretched rubber sheet, if we take that stretching to an extreme so that even light can't escape, that's our idea in Einstein's universe of what represents a black hole. And if you could take a black hole and move it close to the speed of light, which is 186,000 miles per second, the ultimate speed limit in the universe, then you would shake space and time so much that you would generate gravitational waves. Again, think of what would happen if you drop a heavy ball onto a trampoline. The trampoline will wobble, and there'll be ripples spread out across the surface of the trampoline. That's essentially what gravitational waves are, ripples in space and time themselves produced by very massive objects moving very, very fast. Now, technically, if I wave my fist, I'm generating gravitational waves. But I can't move my fist at 186,000 miles per second, and it doesn't weigh the same as a star. And that means the gravitational waves I can produce are far, far too weak for us ever to measure. So instead, we need to use the cosmos as a laboratory to measure gravitational waves. The kinds of objects that would produce these ripples in space and time caused by changing gravitational fields are going to be objects with extreme gravity. So my talk really does belong in a session on extreme science and extreme technology. The kinds of events we're talking about are exploding stars or colliding black holes, or perhaps even the Big Bang itself. The trouble is, however, those gravitational waves, just like ripples in a pond, become weaker as they spread out through the universe because they go in all directions, and we just intercept some of that gravitational wave front. And in fact, to detect them, and Einstein knew this, requires measurements here at the Earth, which are unbelievably tiny. Measurements to the distortion in our patch of space and time, which correspond to less than 1,000th the size of a proton, the little particles that you get inside the centers of atoms. Now, maybe you don't have a good idea of how small a proton is. Let's think of it another way. It's about 1/1,000,000th the width of a human hair. So that's really small. Now, how are we going to detect distortions as small as that? The remarkable thing is we can, and we have. And that was the big story that we announced to the world in February. We did it using the LIGO Laser Interferometer Gravitational Wave Observatories. And these are kilometer-scale instruments, the arms of which are about 4 kilometers or 2.5 miles long. And there's one in Louisiana and one in Washington State. What you would have seen is a flyover of the LIGO site, and essentially what that would show is the size of the detector. So what this animation is supposed to show is two beams of laser light heading at right angles to each other, reflecting from a mirror, and as they recombine, when they come back from the mirrors, they will undergo what we call interference effects. This is an effect caused by the waves of the lasers getting out of step with each other. So in other words, if the distance traveled by the laser that goes to the left is different from the distance traveled by the laser that goes to the right, when they recombine, they won't be in step with each other, and that means you'll see what we call destructive interference. You can also have them interfering constructively, and basically that will depend on whether there's a difference in the path traveled by the two lasers. When the change in the path length occurs, then the interference pattern shown by the laser light will also change. And what that will produce is an effect that we can look for. Except, of course, it's really, really small. So that's why we need our LIGO detectors to be large, and we also need to bounce the laser beams back and forth hundreds of times within the arms of the detector to increase the path length traveled and make us more sensitive to those tiny changes. What this shows is a cartoon illustration of the merger of two massive stars. Not black holes this time, but what we call neutron stars. Very massive stars, but a little bit less massive than a typical black hole. And the ripples spreading out, the gravitational waves that we've referred to, basically, those will be produced during the final moments before those two neutron stars merge together. And that means the kind of signal we're looking for is shown here in the form of a graph. What that signal shows is a pattern where the frequency of the gravitational wave, the number of cycles per second, increases very sharply just before the massive objects merge. Now, in the bottom left, there's a little sound file. I don't think it's going to work, but that's no problem, because in any case, I was going to get everyone here to make their own gravitational wave sound. Gravitational waves are not sound waves, but the frequencies produced by typical neutron stars or black holes correspond to frequencies that our ears can hear. So that's why I called my talk Listening to Einstein's Universe. So we can represent the gravitational waveform that we expect to see in the form of the graph, but we can also represent it as a sound, and we call them chirps. And it sounds a little bit like this. It's a rising pitch, rising frequency, and also it gets louder just before the objects merge. So I'd like to invite all of you to join me in a gravitational wave symphony to make that chirp sound. We'll do it on the count of 3. We'll all do it together. 3, 2, 1. Excellent. Well done. So that's what theory had been telling us for a long time, the sound that we wanted to listen for. But because the effect is so small, then detecting it was going to be tough because of all the other noises that get in the way. Disturbances which are not to do with colliding black holes or exploding stars, but just disturbances down here on Earth that could mimic or indeed swamp the effect of a gravitational wave signal. So that's why we built 2 LIGO detectors, because one of the key ways that we could be sure that we had a real signal from up there and not just some local disturbance is if you saw the same signal at essentially the same time here on Earth in both detectors. Actually, not exactly the same time, because it takes a few milliseconds for a gravitational wave to travel the distance from Louisiana to Washington State or vice versa. So, over the last couple of decades, we've built a number of these detectors around the world. 2 in LIGO, also one in Europe, which my group in Glasgow has been heavily involved in, called GEO. Another one in Italy called Virgo, and a facility in Japan, which has recently been upgraded, but in the last decade was a smaller facility. It's still under construction, but they've now made it much larger. Bottom line is, we didn't find anything. Believe me, if we had, you would have heard. So by 2010, we had recognized that the initial generation of gravitational wave detectors were just not quite sensitive enough. And frankly, that's what we expected, because we knew these signals were very weak. So that initial generation was to test the technology. And then in 2010, we began embarking on upgrades. LIGO 2.0, or Advanced LIGO. What we wanted to do was to increase the sensitivity. And as you can see, our group in Glasgow was one of a number of groups involved in the research and development to make all of that possible. So one of the main things we wanted to do was to boost the power of the lasers so that the signal would be more sensitive, to enhance a lot of the vacuum systems to isolate, again, the gravitational wave detectors as best we could from the surrounding environment. And perhaps most crucially, in terms of the event that we did detect, which I'm just about to tell you about, what we wanted to do was to suspend those mirrors in a manner that would isolate them from local ground disturbance. So in initial LIGO, they were suspended on metal wires, like piano wire. But in advanced LIGO, they were heavier mirrors, and they were suspended on glass fibers, silica fibers, making them among the most stable and isolated places on Earth, where the ground shaking, well, it just basically wouldn't have an effect on the stability of these mirrors. Now, all of that made the detectors sensitive enough, we hoped, to see something. And we were good to go in September of 2015. We were primed to begin our first science run on September 18th. But in fact, we were basically ready a few days before. Now, if you listen very carefully, you'll maybe just be able to pick up that little chirp sound, just like you all did. But of course, there's rumbling and noise. In fact, this is two versions. One where we've shifted the frequencies to higher frequencies to make it a little bit easier to hear. But of course, even with what you can see, there's that characteristic behavior of a rise in pitch, a rise in frequency towards the very end. The other thing I should add is that, of course, we're running the movie again and again. Nature wasn't so kind to us because the real event was basically over in about 0.2 of a second. It would have been a whole lot easier to detect if we'd kept getting that signal again and again. So what did we learn from that 0.2 of a second? Well, that's what we announced at the press conference in DC on February the 11th of 2016. The National Science Foundation were very proud to present that press conference because the NSF had invested in this project over decades. And basically, when a lot of people were saying, oh, you'll never detect gravitational waves, it's just too difficult. But we did it. And the opening remarks of the press conference by the executive director of the collaboration, Dave Reitze, were, ladies and gentlemen, we have detected gravitational waves. We did it. So we absolutely opened the press conference with the punchline. And what a punchline it was. These signals are from the paper that we published. And you can see the lower panel shows that upward rising chirp, just like we were hearing before, and indeed you replicated a few minutes ago. And the top two panels show the signals from the two detectors. And sure enough, they look almost identical, just as they should if it's a real gravitational wave source. And then the middle panel, we've done a little bit of reconstructing to essentially allow us to compare with the predictions of Albert Einstein's theory of general relativity, his theory of gravity. And again, Einstein's theory passes the test. Einstein was right. So, I think he can feel quite pleased with himself. There was a great media furor about this event. And one of my jobs for the collaboration was to help coordinate those efforts. And it included a social media campaign, and our Facebook and Twitter posts were shared millions of times around the world. So what did we learn? What exactly was this event? Let me just leave you with a few remarks about that. It was the merger of two massive black holes. One 29 times the mass of our sun, and the other one 36 times the mass of our sun. They collided together. The final moments of that collision, lasting just a fraction of a second, released the gravitational waves that we detected. Now, we weren't able to determine the position on the sky of those black holes very well, because with only two detectors, we really can't be very sure which direction the black hole's gravitational waves came from. So this colored arc in the sky, shaped like a banana, overlapping with the Milky Way, is the best we could do. But in the future, with more gravitational wave detectors, we'll be able to triangulate the position of future sources much better. And that will allow us to go look with conventional telescopes, optical telescopes, and see what we see. But in fact, it's entirely possible that this event didn't give off any form of light whatsoever. There's a few suggestions that maybe it gave off some gamma rays, but it's really basically gravitational wave energy that was released in the event. It happened a long time ago in a galaxy far, far away. As we heard from Bob, more than 1 billion light years away. Now, wonderful, the movie's working, thank you guys. So what you see here is a simulation based on the information we were able to obtain from the gravitational wave event. And it shows the final moments of those two black holes merging and becoming one black hole. And the final black hole had a mass of 62 times the mass of our sun. Now wait a minute, I can hear you say 65 and 62 aren't the same number. Where did the missing 3 times the mass of the sun go? That's what was released in gravitational wave energy. And it all happened in 0.2 of a second, which means, if you do the math, then more power was released in gravitational waves in that 0.2 of a second than all the light power from every star in every galaxy in the entire observable universe. And all of this was coming from the dark side of the universe that doesn't perhaps give off any light at all. So I think it was Darth Vader who said, never underestimate the power of the dark side. And I think our detection very much confirms that. So this was all over the news. It even featured on The Late Show with Stephen Colbert, and indeed Saturday Night Live. And it's been a huge story in all sorts of ways. In fact, you can even now obtain a gravitational wave dress. I'm not sure if that would work well for me, but I'm just waiting for the kilt to be produced, and I'll be buying that. All of this basically means gravitational waves are really now on the map. So if you want to watch our new field of astronomy unfold, as hopefully we make many more discoveries, you can follow us on Twitter. You can follow us on Facebook. Thank you.
All right, thank you once again, Prof. Hendry. Thank you.